Okay, I'm going to give you guys some notes on friction. Some of this is going to be a review of what we did on Tuesday, but since it's been a couple days since we've seen each other, I'm going to review some of that stuff. We finished our class-wide friction lab on Tuesday. We started to summarize some things. We tried to figure out what are the factors that affected friction when you're sliding a block across, a wood block across a wood surface. And we changed the mass of the block. We changed some other things like the texture of the surfaces in contact, etc. But let's first talk about the different kinds of friction. So there's kinetic friction and there's static friction. Okay, so kinetic friction is a friction between two surfaces that have relative motion between themselves. Sorry, I didn't finish that word. Between themselves. Static friction is friction between surfaces that have no motion between them. So static, think of two things that aren't moving, but there's still friction between them. Kinetic friction always opposes motion. So when something's sliding, friction is always in the opposite direction of the motion of the object. But static friction can oppose motion, or it can be in the same direction as the motion. So static friction can go in either direction. The example I gave of when static friction actually is in the direction of motion would be if you left your backpack on top of the roof of your car, you got in the car and started driving away. At first, the backpack stays in contact with the roof of your car because static friction is holding it there, moving it, accelerating it from rest to start moving with the car. So you'd have to draw a force diagram with friction in the direction of motion in that case. Friction depends on two things. It depends on the normal force, as we discovered in our lab, and it depends on the surface texture between the two surfaces in contact. Those are the only two things that friction depends on. It does not depend on the surface area, and it does not depend on the speed of the object. So no matter how big or how small the surface areas are in contact, the normal force and the surface texture are the only things you need to know to figure out what the friction force is. So the friction equation, and I think we probably had this on the board at the end of class on Tuesday, is for kinetic friction, Fk is equal to mu k. Remember, that's the Greek letter mu. That's called the coefficient of friction. It's got no units. It's a unitless coefficient. Times n, which is the normal force. Okay? I like to always say, you're going to hear me say this a lot, physics is fun. F-mu-n. Kind of looks like a U. So I say physics is fun, right? So that friction force on the left side of the equation, this is just the force of friction in newtons. The normal force is also in newtons. So this coefficient of friction is unitless. And mu k is always pretty much between 0 and 1, as I talked about in, can't be equal to, just greater than 0 and less than 1 almost always. It's smaller for surfaces that are smoother, less rough. Okay? So rougher the surface, the closer to 1 mu k is going to be. I think in class we had a mu k between the wood surfaces of like 0.27 or 0.28, something like that. So that was for the lab that we did in class with the sandpaper and the wood surface. We also have static friction. And the equation for static friction is very similar, but not exactly the same. For static friction, it's less than or equal to the coefficient of static friction times the normal force. It's only equal to this. It's only equal to this when it's at its maximum. And the reason that is because static friction is a lazy force. It only does as much as it has to do to keep an object at rest. So that's kind of like you guys. You guys are kind of lazy. You don't like to do stuff you don't have to do when your parents ask you, right? But you do it if you have to do it. That's how static friction acts. I'm going to give you an example on the next slide of what I mean by a lazy force. But once an opposing force exceeds static friction's maximum value, the object begins to move and kinetic friction takes over because there's now motion between the two surfaces. So now you have kinetic friction. So in our lab, you saw that as Jacob was pulling on the block with the force sensor, the force was going up and going up and going up and going up as time went by, still not moving. And then all of a sudden, the block broke free. That was when static friction was at its maximum, and immediately the force drops down, and it's pretty constant. It was a little, bumpy, but it was pretty constant. That's the kinetic force of friction. And the static force of friction, sorry about that, the static force of friction max, the maximum value of static friction, is always greater than the force of kinetic friction. Think about, it's always harder to get something moving than to keep it moving. That's because of the electrostatic attraction between the two surfaces. Friction is caused by electrostatic attraction between surfaces. And you're breaking that bond between the atoms to get the object moving. And while it's moving, those atoms are still attracted to each other, but they're not kind of locked in as they would be. The attraction isn't as strong as when their two surfaces are at rest. Surface molecules. Okay. So here's an example of how static friction is a lazy force. So we got Chad pushing this 50 kilogram crate. He's got a 100 Newton force that he's pushing it with. We want to figure out what is the force of static friction when Chad does that. I meant to use my highlighter for that. What's the force of static friction when Chad pushes that thing? So we're going to draw a force diagram first and foremost. So let's do that. So you've got Fg down. That's always the first force that we label. And it's a 50 kilogram box, 10 newtons per kilogram. So it's a 500 Newton force of the Earth pulling down. Now you've got the normal force going up. Normal force should be equal to that downward force because there's no acceleration in the vertical direction. It's a balanced force diagram vertically. No acceleration that way. So that's going to be 500 newtons. Then you got Chad's push. I'll draw that a little bit shorter there. Chad's push of 100 newtons. And you've got some friction. Static friction, we'll say. And we got to figure out what that is. All right, well, so you've got a formula for the force of static friction max. It's mu s times the normal force. And if you remember in that slide before, the coefficient of static friction that I gave you was 0.35 between the two surfaces. 0.35 times the normal force, which is 500 newtons. So that's going to be 175 newtons, if I did my math right, which means that the Fs max is 175. So you'd be tempted to say, okay, the static force of friction is 175 newtons. But that makes no sense because look at the force diagram now. Chad is pushing with 100 newtons and you've got 175 opposing his push. That means there's an unbalanced force back into Chad of 75 newtons. So clearly that's not what happens. When you push on something, it doesn't fly back in your face, right? So this is what I mean that static friction is a lazy force. If Chad pushes with 100 newtons, then the maximum, or the static friction, I should say, sorry. Static friction at that moment is 100 newtons. So for the answer to this problem, the answer is 100 newtons. Let's say Chad pushed with 125 newtons. Well, static friction is going to respond. It's lazy. It does only what it has to do. It responds with 125 newtons to keep the object at rest, static. You push with 150. Chad pushes with 150. It goes up to 150. When Chad pushes a little more than 175, now the object is going to move, and now it breaks free, and kinetic friction takes over at some lower value, which we don't know because I didn't give you mu k. So we don't know what mu k is, but we know it's going to be less than 175 newtons, and there'll be some acceleration to the right. So that's what I mean by static friction being a lazy force. Problem from worksheet 5, which is going to be your homework for tomorrow. This is the third problem on the worksheet. I'll do this with you so you kind of see how this works, and then you should be able to do this worksheet on your own. So there's 120 Newton force applied parallel to the floor to a 55 kilogram student who's at rest on the floor. The coefficient of friction is mu k equals 0.14. So I'm going to write down everything I know here. Actually, let's make a force diagram first. So we're going to draw a force diagram of the situation, which is going to be the student, because we're applying a force parallel to the floor to a 55 kilogram student. So we're applying a force applied, 120 newtons, to a kid who is 55 kilograms, so 550 newtons, which means his normal force is 550 newtons. And there's some friction force that's going to oppose this. It's going to be kinetic, I think. So because they give us a coefficient of kinetic friction, mu k, 0.14. So I want to figure out what that force of kinetic friction is. I'm going to use my friction equation that we just learned. Physics is fun. F mu times n. So the calculation of the static or the kinetic force of friction is 0.14 times 550. I get 77 newtons for that. Okay, so they ask for the acceleration of the student. Well, you know the acceleration is F unbalanced from Newton's second law divided by mass. What's the unbalanced force? I have to come up with an equation for the net force. So F net or F unbalanced, however you want to say it, is a difference between the bigger force in the horizontal direction and the smaller force, which is friction. So this is no different than any other problem we've done with friction, except now we actually know how to calculate friction. So we did this equation for the first time to get a number for friction instead of the problem just giving you friction. All right, so this is 43 newtons, and I divide that by the mass. So I'm going to have acceleration is 43 divided by 55. I get 0.78 meters per second squared. Okay. And now they say resting on a carpet with a coefficient of static friction of 0.3 is 120 Newton force sufficient to allow the student to accelerate. You're going to have to figure that out by calculating the maximum force of static friction and seeing if that is bigger or smaller than the applied force to the student, 120 newtons. If the static force of friction is bigger than 120, the kid won't move. If the maximum force of static friction is less than 120, then 120 is enough to get the kid to move, all right, and accelerate. So answer that question on your own. All right, I hope that helps you guys. I want you to do worksheet 5 for Friday by the end of the day. Thanks. Have a great weekend.